All right. Hello, everyone. You're welcome back to our class, Chemistry International. It's a pleasure to have you back on board today. Without wasting any of our time, we're going to be continuing from where we stopped in the last class. And this is basically electrolysis. We've done justice about 1 or 2 classes concerning this topic. But then even at that, after this class, probably we're just going to stop there and receive feedbacks from here and there concerning the contents of the video. Like we have been saying, if there's any question, comments, addition, elimination, subtraction, substitution, whatsoever, please feel free to add it in the comment section. So today we want to look at calculations in electrolysis. We want to look at calculations in electrolysis. Beyond reasonable doubt, there is no way you can talk about electrolysis without talking about, there's no way you can talk about calculations in electrolysis without talking about, Faraday's laws of electrolysis. So in this class, we expect to learn and understand Faraday's laws of electrolysis and then how to apply these laws in solving different problems. Michael Faraday in 1833 proposed 2 different laws. He is an English scientist, chemist, who talks about the relationship between light and electromagnetism. We are not going there tonight. So what we are actually looking at is calculations in electrolysis. And like I said, we cannot discuss calculations in electrolysis without talking about Faraday's laws. Faraday's laws. They are basically 2 laws. Briefly speaking, the first law, you've got to know the definition, understand the content, and then apply it in solving problem. The second law, the same thing applies to it. So Faraday's first law states that the mass of the substance discharged during electrolysis is directly proportional to the quantity of electricity passing through the electrolytes. For instance, if this is an electrolyte, all right, electrolytic cell, for instance, you have copper sulfate, Cu2 plus and SO4 minus, and of course, our electrolyte has to be in molten form or in aqueous state. So if it is in aqueous state, you've got to have your water. Do we understand? You've got to have your water. So if you have water and copper sulfate, basically, and there is supply of electric current into the electrolytes, the amount or this mass of this copper 2 plus that is being discharged to become Cu2 plus 2E minus to give you copper solid aqueous states, the mass of this guy being discharged is proportional, is determined by the amount of electricity that is being passed through these electrolytes. So mathematically, mass is directly proportional to the quantity. In mathematics, when you're talking about variation, you introduce the constant of proportionality. So M is equal to ZQ. At times they might use K. They might also use capital letter E, where M is the mass of a substance discharged, Q, the quantity of electricity passing through the electrolyte, and Z, the electrochemical equivalence. Furthermore, this quantity of electricity passing through the electrolytes is given as current times time. All right, to know the amount of quantity that passes through these electrolytes is by knowing the current that the supplier, the energy supplier, contains, and the amount of time that the current passes through the electrolytes. Do we understand? So invariably, what we're saying is that this mass is equal to ZIT. This mass is equal to ZIT. This is Faraday's first law of electrolysis. In that case, if you are looking for the quantity of electricity being discharged, all right, quantity of electricity that passes through the electrolyte, you've got to need the current and the time it takes for the electric current to pass through the electrolyte. The time it takes for the electric current to do what? To pass through the electrolyte. And also, of course, this is Faraday's first law, but like we have almighty formula in quadratic equation in mathematics, we also have almighty formula in calculation under electrolysis. And this almighty formula is simply take as this M is also equals to Mr. IT all over CF. This M is equal to Mr. IT all over CF, where M retains its conventional usage mass. MR is relative atomic mass, current in ampere, T in time in seconds. This C is the charge on the ions. All right. For instance, Cu 2 plus the C is equal to 2. Fe 3 plus the C is equal to 3. Cl minus the C equals to 1. It doesn't have to, this charges does not affect the value. We only need the number of ions, irrespective of whether it is plus or minus. And this F is Faraday's constant. Faraday's constant, which is what? Which is 96,500 coulomb per mole. Faraday's constant. Now, M is equal to Mr. IT over NF. If I want to have similar thing on both sides of the equation, what that simply means is that if I want to have numerator and denominator here, I can bring this relative atomic mass or molecular mass to be the denominator here. And invariably, that simply means you can call this equation 1 M over MR equals to IT over CF. M over MR equals to IT over CF. You can take this as equation 2. All right. Now, from your mole concepts, there's somewhere I'm going to here. From your mole concept, you and I know that number of mole is equal to reacting mass or atomic mass, as the case may be, all over molecular mass. In any case, it simply means that we can change this guy here for this number of mole. Of course, this same number of mole is equal to concentration times volume. This same number of mole is equal to volume all over 22.4 gm cube. If you do not forget from your year 10 SS1 chemistry, this same number of mole is equal to number of particles. Number of particles over Avogadro's constant, 6.02 times 10 to the power 23. Particles in this case can be atoms, ions, or molecules. AIM, number of particles. So it simply means instead of mass over molecular mass, I can introduce this guy. All right? Because there are some questions that you're going to be needing volume. The question has to do with gases. You're going to be asked to measure or to calculate the volume of the gases that evolved during the electrolysis. Remember, part of the uses of electrolysis is that it produces compound. It is used to produce gases or even compound, as the case may be. So It therefore means this guy can be replaced with any of this guy. But because we're talking about gas, we are going to specifically replace this guy with this. It simply means volume all over 22.4 equals to what? IT all over CF, equation 3. All right? So we are done with anything that happens to do with Faraday's first law. As for Faraday's second law, this simply states that in an electrolysis that involves more than one electrolyte, the number of moles of the substance discharged is inversely proportional to the charge on the ions of the elements. In this case, we are talking about having more than one electrolyte. You are passing the electrolytes, what have you? You are sending the same amount of electricity into the two electrolytes, or even more than two electrolytes. According to Faraday, he was able to, infer from his own experiment that the number of moles, the amount of the substance discharged, is always inversely proportional to the charge that the ion of the element carries. All right? It therefore means the higher the charge, the lower the number of moles of the elements being discharged. So invariably, just like we did in first law, number of moles is equal to, we introduce the constant of proportionality, C. And then we have K is equal to NC. It therefore means at any point in time, the number of mole, the amount of any element being discharged multiplied by the charge of the ion, in as much as the same amount of electricity is passed through the two or more electrolytes, is always equals to the second number of moles times its own charge, and so on and so forth. So we are going to be applying this in solving problems. Of course, we are going to be applying these different equations in solving problems.